Hello everybody. In this video we are going to see how to use OpenCV in Flutter applications. We are going to use OpenCV in C++ and we are going to reuse an OpenCV code that already is working on Windows. So the code that we will be using is this code for the Aruko detector. These are Aruko markers. It's markers that mainly used for augmented reality applications. And we have our custom Aruko detector, and we are going to run it on Flutter. So this is our Aruko detector. Now we are not going to get into the Aruko detector code. There is a separate tutorial about writing a custom Aruko detector. I'll put a link to the repository, and there is also a YouTube video. So essentially, we are going to take this Aruko detector CPP and Aruko detector H file and use it inside Flutter. So let's get started. I already created a Flutter application. This is the Flutter application, some template. What we have is a main page with a button. When pressing the button will take us to another page, which is the detection page. In the detection page, I already set up the code for opening the camera and reading camera frames. So we have the camera controller, we have an Aruko detector, and then in initializing, so this is where we initialize the camera. This is just setup code. When we initialize the camera, so we take the back camera, and then we just create an instance of the camera controller. As for the image format, so for Android, we are asking for the YUV420 image format, and for iOS, we are asking for the BGRA image format. Then we initialize the camera controller, and this is where we register for receiving the preview camera frames so we can process them, and we will use the process camera image for that. So in the process camera image, this is where we are going to run the Aruko detection. There is some safeguard code here, so making sure that we are mounted, and we will run the detection every 200 milliseconds. We will test. Maybe we will take this. Maybe we'll take this slower. And then we call to the Aruko detector our detect method. And that's it for the template. So let's take a look at the Aruko detector. So this is the Aruko detector. Currently, this is just an empty class. We have a detect method which receives the camera image and the image rotation, and the response is going to be a list of Aruko markers coordinates. And in order to draw the markers on the screen, we have the detections layer. So this is our detections layer. It uses a custom painter. So we have this Aruko's painter. And the Aruko painter will not go over the code, but basically it gets a list of Aruko coordinates. So for each Aruko we get 4 corners, and each corner has X and Y. So for each Aruko we have 8 numbers, and that's what we do. We just loop over all the Arukos, and we are drawing. Here we are drawing line from one corner to the other. So we are going to draw a line from the top left corner to the top right, from the top right to the bottom right, from the bottom right to the bottom left, and again from the bottom left to the top left corner. So this is just this code, nothing special here, just painting squares on the screen. If we go back to our detection page, one more thing that is of importance. We have the camera frame rotation. So when we receive the camera frames, the preview frames from the camera, so for Android, the preview image can be rotated. So in order to know the rotation of the preview image that we get, we take the sensor orientation from the camera. And for iOS, at least in my testings, in iOS, the frame that we get from the camera, the preview frame, is always in the upright position. So so there is no need to take the sensor orientation. So this is our template application, and the next thing is we are going to create a plugin, and inside this plugin we are going to write our OpenCV code. So this is our project folder, Flutter OpenCV stream processing, and we have the OpenCV application. This is this application that we just saw, and now we are going to create the plugin. So this is our plugin. We are going to name it native OpenCV. Okay, it's ready. So let's get into it. And the next thing that we want to do is actually copy the Aruko detector classes. So any C++ code that we want to use in Flutter, we have to put it under the iOS folder and the classes. The reason is that we are going to use Cocoa Pods in order to build this plugin as framework, and in Cocoa Pods we can reference code that we can't reference code that is above the pod spec file. This is why we are going to put all the files in the classes, and the plugin template already created these classes folder for us. So we have that, and we are going to create a directory. We will call it Arauco Detector, and let's copy the files. So on my computer it's here, and we have the H file and the CPP file. Next thing, we are going to create our plugin code. So inside classes, we are just going to create a file native OpenCV.cpp. So in this code, we are going in this file, we are going to put all our plugin code. And next thing is for the Android. For Android build system, we need to create the CMake list file. So under Android, we are going to create the cmakelist.txt file. Okay, and now we can open the project in Android Studio and start preparing the Android integration. So here is the Android Studio, and the project that we want to open is the native OpenCV. This is our plugin. And then under example Android. So we are not opening the Android folder of our plugin, but we are opening the Android project that is under the example. The example project is already set up to have both the example code and our plugin code. So this is how we should work on it. So the initial Gradle sync finished successfully, and now we are going to switch from the Android view to the project view. And this is the example code. This is our plugin code, Android. This is native OpenCV. We have the CMake list file. So we are going to copy the CMake list. Now, I'm not going to get into how we integrate OpenCV into Android. There is actually another video on that. But basically, what we need is, first of all, we need to download the OpenCV Android SDK. So in the releases pages of opencv.org, you download the Android SDK, and you extract it to some folder on your machine. Then I defined the global environment variable on my PC. I called it OpenCV Android, which points to the SDK. So we can see here. And if we'll take a look, so our environment variable just points to the root of the SDK, and then the OpenCV directory is under SDK native JNI. Okay, and here we have the make files for OpenCV. So we define that, and then we are creating the native library for Android. So we're going to call this library native OpenCV. This is going to create the lib native OpenCV shared object, basically DLL for Android with our C++ code. And here we are providing the C++ code that we want to include in our project. We have the Arauco Detector CPP, and we have our plugin CPP, the native OpenCV. Here we define the include directories, like where we have the H files. So again, it's in the Arauco Detector directory, and this is where we are linking our shared object, our like DLL. So we link it using the OpenCV libs. So this is our CMake list, and now let's resync Gradle again. So let's see the result. Okay, now we need to actually use this CMake list in our project. So we go to the build Gradle, and here we tell it to use external native build and use the CMake list. And now we want to sync Gradle again, and now it's going to configure our project using this CMake list file. Okay, so although it says build successful, if we scroll up, we can see that we got the OpenCV found false, so we can think that it didn't find the OpenCV. But if we scroll up, we see that the actual error is that the minimum required SDK level for OpenCV is Android 21, and here in the build Gradle, if we look, the min SDK version is 16. So I'm going to change it here to, I'm changing to 24. So this is for our plugin, and I will do the same for the example code. It's not really necessary because we are not building the actual example code, but if we are here, let's do it. So min SDK version, we are going to use 24, and the target SDK version I'm going to change to 31, and let's see if we have compile. Yeah, compile SDK version will change to 31 as well. Now we are going to sync Gradle again. Okay, successful, no errors. We will switch back to the Android view. Under the native OpenCV, under our plugin, we can see that now we have the C++ folder, and in the C++ folders we have the Init Detector and the native OpenCV CPP. This will be our main plugin files. So from this file we are going to expose the API to Flutter. So I will copy here some initial code. What we have here, this is just a utility function to rotate OpenCV matrix, and this is how we expose functions. This is how we expose function to Flutter. So we are working using what's called the Flutter FFI or Dart FFI. This is the documentation how to build native code using Dart FFI, and so we created the plugin, then we added the C++ source, and here we have this example. So any C++ function or C function that we want to expose, we have to have this extern C and this attributes. So this is what we did here, and this is a simple function that just return the OpenCV version, and we return it as a string. So this is the first function that we are going to test against. We are going to try to call this function from Flutter, and if it works, we know that our setup is correct. So now we are going to open the Dart side, or not to say the dark side, of our Flutter plugin. So here we are going to open it in Visual Studio Code. So this is the Dart side of our plugin, and like this is the Android side of our plugin. So in this code, we are going to okay. So what we do here, let's import library.ffi, and we need to have FFI as a dependency, so to our project. So here we add a dependency FFI, and version 112, I believe, is the current version. Okay, platform.io, UTF-8, this is from the package FFI, so this is the FFI types. Okay, so the first thing that we need to do is to load our native library. So in Android, this is going to be the libnative OpenCV. This is the library that we are building in Android, and this will be a dynamic library. On iOS, the C++ code is actually going to get built statically into the app. So we are just using the current process. This is a native lib, and now in order to get a reference to the C++ functions, we will use the native lib lookup function. And the way that the lookup function is working, the first thing we need to provide the function name that we are searching in our native code, either in the libnative OpenCV or in the current process. So this is the function name, and then we need to provide the API, or rather the signature of the function, like the C++ or the C signature, and the corresponding Dart signature that this function will have. And this is what we define here. So here what we are going to define is the is the C signature of our method. So if you remember our version method, it has no parameters and it returns a string, and the string it was just a pointer to a character. So this is a pointer to UTF-8, and the Dart function of our method is basically is going to be the same, no parameters, and it's going to return a pointer to UTF-8. Okay, so note we are not returning here a string because we need to use it's actually a pointer, it's not a string. So this is a pointer to UTF-8. Then we can call to the lookup function, and with the lookup function, okay, we are looking for a function named version. This is the signature of the function, and we want to map it to this Dart function. And this is if it finds the function, so this version will be the actual function. And here we have our native OpenCV class. So this is the class that we are going to instantiate from our Flutter application, like from the OpenCV app. We are going to create an instance of this class. The method channel is not relevant in our case because we are not communicating with the Android platform. We are just working with the C++ level. So this is just a demo function, and this is the function that we are exposing to the OpenCV app. So the OpenCV app will call to the CV version function, and what we are going to do, we are going to call to our native function. This is this version, and there is the response of this version is, as we defined here, is a pointer to UTF-8. So a pointer to UTF-8 has a toDart string method. So this is how we convert the pointer to characters into a Dart string. So this is how we expose the method to the Flutter applications. And speaking about the Flutter applications, so let's go to our OpenCV application, and let's use our plugin. So in the pub spec, we first need to add a reference to our plugin. So it is called the native OpenCV, and we are going to use a path reference, which is native OpenCV. So we included the plugin in our code. Then let's go to what's the problem? Native OpenCV. Okay. And running Flutter pub-get. Okay, seems okay. Let's go to our main application and let's use our plugin. So let's do here. Let's create an instance of native OpenCV. So it offers, we import our library. So we have this. What's the problem? Can't define the constructor. Okay. And now every time that we push the button here, instead of navigating, so let's comment this navigation. We will just log the OpenCV version. So you can see that the native OpenCV function, this is our plugin, and this is the CV version method that we expose. So every time that we press the button, we are going to call to our plugin CV version, which is this method, and this method is actually going to call to the C++ version. So now let's say I'm going to start up an emulator on my machine and run our application. Okay, so the app is running, and now we're going to press the button, and we can see that we get the OpenCV version. So it means that our call to the plugin method is working, and inside the plugin we are calling to the C++ application, and it works. So meaning we were able to build our Android C++ library successfully, and also inside our plugin, the Dart side of our plugin, we were able to locate the version function. So our setup is correct. And what we can do next is just go ahead and define all the Aruco functions that we would want to expose to our Flutter application. So we are going to go back to Android Studio. And here where we exposed the version method, we are also now going to expose the Aruko related functions. So let's have a proper indentation, and then these ones, I believe, are from the img proc HPP, and this one is from GUI. Okay, so we have this. So now let's go over the function like quickly. So we have the init detector method. This is where we initialize our detector. Now the way it's going to work, here at the top we define a static variable of the our detector. So we are going to have only one instance per process for this detector, and in the init detector we are going to actually create an instance of this detector. And in order to create the detector, we need to give the detector the marker, like the template marker that we want to detect. And bits, again, this is something that's related to the marker, like how many squares we have in the marker. If we go to our application, our OpenCV application, let's stop it. And under assets, drawable, we have the marker. So this is the template marker that we want to detect, and you can see you can like you can divide this marker into 6 by 6 square, like this is 1, 2, 3, 4, 5, 6. So this marker I call it like that. It has 36 bits. This is something that is needed in order to detect the Aruko marker successfully. So we're going to take this marker, and when we call to the init detector here, we are going to give it the marker. Now, because we embed the image into our application as a PNG, so we are just going to provide the marker here as in its PNG format. And we also provide the number of bytes that we have in this byte array. And here we convert the PNG bytes to an OpenCV matrix. So we do like IM decode, and then we initialize our detector using the marker image and the number of bits. And we also have a destroy detector method, which we just delete the instance of our detector, and the detect method. This is the main method. So let's see what are the parameters for this method that we will need to get from the Flutter application. So we're going to get an image. So this is going to be a byte array of the image. Then we have the width and the height of the image. We have the rotation of the image. And this is regarding the format, whether the byte array represents a YUV image or a BGRA image. And this is going to be an out parameter. This is a pointer to integer, and it has the number count. We will initialize this parameter with the number of Arukos that we found. So if we don't have a detector, we just return an empty array. Then we take the byte array that we got here, and depending if the image is in YUV format or a BGRA format, we convert the byte array to an OpenCV matrix. So this is what we do here. Then we rotate the matrix according to the rotation that we got, so making sure that our image is in the upright position. We convert the image to grayscale, and then we call to the detector Aruko's function on our detector. The result is just a vector of a struct, the Aruko result struct. If you look in this struct, so what it has a vector of points, which is the corners. So for each Aruko we have 4 corners, and then an index. This is something that is not relevant for our example, but if you check the Aruko detector video, you will see that it has to do something with the orientation of the Aruko detector. We are not going to use it. So we got a result, which is a vector of all Arukos that we found on the image, and now all that left to do is just iterate over all the Arukos. And for each Aruko in the result, we are just going to push all the corners. So we have 4 corners, and for each corner we have X and Y. So we just push these coordinates into our output vector, which is just vector of floats. Once we done with that, we need to convert this vector of float into a float array, float pointer, because this is our this is what we return from this method. So this is the way we do it. We just we allocate a chunk of memory using the number of elements we have in this array, and then we copy the memory from the vector into our float array. And before we return the float array, it's important that we initialize the out parameter with the number of elements that we have in the array. So on the Flutter side, when we get this float array, we also know how many elements we have in this array. And let's build the project. We'll see if everything compiles here. So I'll pause the video. Okay, so the build was successful, and if we scroll up a little bit, we can see here that it compiled our detector. Now, one important thing that I want to mention here, this C++ code is exactly the same code that is going to get built on iOS. The reason that I'm working inside Android Studio is only because I'm a Windows user, and it's more convenient for me to work inside the Android Studio. But if you are a Mac user, you can certainly work on this file in Xcode. This is not a problem at all. This is a cross-platform code that is same code going to run both on Android and iOS. So the next thing is going to be exposing this or using this method in the Dart side of our plugin. So this is our plugin code, and now we want to get reference to the method that we defined in C++. So as you remember, we have first to define the signatures of the C functions, then define the signatures for the Dart functions, and then we are going to look up the functions in the native library. So as for the C functions, this is going to be our functions. So let's go over the signatures, like how we define the signatures. So the Init Detector, we return nothing, and the parameter is the marker image. So this is a byte array, and the byte array is represented as a pointer to uint8. We also send the size of the byte array, and this is going to be an integer. And note that we are using int32. So this type is from Dart FFI. Okay, so this is an FFI type, and the number of the hardcore marker bits is also int32. So this is the Init Detector. The destroy function has no return value and no parameters, and our detect method. So the result is a float array. So this is a pointer to float, and the parameters are the width, the height, and the rotation. These are all int32. Then we have the image, which is a byte array. So it's a pointer to uint8. The format, whether it's YUV or not, this is Boolean, and the out parameter is a pointer to integer. So again, this is pointer to int32. And again, note that all the types are from Dart FFI. Also, this Boolean is from Dart FFI. So this is the C signature of our function. Now we define the corresponding signature in the for the Dart functions. So this is it, and we can see that for the Init Detector, so the marker is a pointer, so we're going to use a pointer to uint8, but the size and the bits are just regular integer, that like the integers that we are using part of Dart core. Okay, and this is the mapping between int to int32. This mapping is going to happen automatically. Destroy detector has no return method, no return value, and no parameters. And the detect method is going to return a pointer to float. And again, all these parameters, we use the types from Dart core. So the Boolean is from the Dart core, as opposed to the Boolean here, which is from Dart FFI. And the last thing that we need to do is just look up the functions. So this is the lookup functions. So again, the lookup, we are looking for the function inside the native library, and we look up the method by the name of the method and by the signature of the method. Now, all we need to do is just expose this method to our Flutter application inside our native OpenCV class. So these are the methods. Let's do some imports. Okay, and image buffer that we have here missing. This is going to be a global variable that we are going to use. So on every detection, we will need to copy the Flutter, the image that we get from Flutter, from the camera. We need to copy it to some memory buffer, and we don't want to allocate this memory on every detection. So we will just define here a global buffer that we will allocate once and reuse. So let's see the methods. So the Init Detector. So this is how we are going to get the marker. We are going to get it as a Dart type of uint list, and now we will have to convert this uint list to a pointer, or rather we're going to call the Dart function to a pointer of uint8. So how we convert from uint list to pointer of uint8? The way we do it is first of all we need to allocate a memory. So we are calling to malloc allocate, and we are allocating using the total size that we have in the list. This returns a pointer to uint8. So we got the pointer. Now we need to copy the buffer from here to our image buffer. And the way to do it, so we take our buffer and we get a reference to this buffer using a uint list. So if you can see, as type list, just create a type list view backed by memory in the address space. So this method just returns us a uint list that actually maps to the exact same memory that the image buffer is pointing to. So these bytes and this image buffer are essentially pointing to the same memory address. And the reason that we want to use the uint list interface is because it has a set all method where we take our marker PNG, which is a uint8 list, and we can copy the buffer from it to our bytes. And again, the bytes and the image buffer are pointing to the same memory. So when we are copying the buffer to our bytes variable, it's essentially copying the bytes to the memory that is pointed by this pointer to uint8. So now having this img buffer, we can call to the Init Detector method, passing the image buffer, the total size, and the number of bits. And once we initialize the detector, we allocated here some memory, so it's important to free the memory that we allocated. So this is the Init Detector. The destroy is quite simple because we have no return type and no parameters. So we just call to the destroy detector, and in case we initialize the global image buffer variable, we also we are freeing this memory. And now let's look at the detect method. So the detect method is going to return a list of float 32. And this is the parameters that we will get from the Flutter application. So the width and height of the image, the rotation of the frame, and then we are going to get 3 buffers, the Y, U, V buffer. Now, if you remember, in Android, the image format is YUV, so this is the 3 buffers that we get for the YUV. And on iOS, the image is going to be a single buffer, which is the entire BG array. So on iOS, only the Y buffer will be present here, and these two are nullable, will be null on iOS. So if we look at our detect method in C++, this is the detect method. We need to pass the image, this is the image bytes, as a pointer to uint8. So what we need to do is again take these 3 buffers and combine them into a single pointer to uint8. So this is what we are doing. First of all, we are calculating the total number of bytes that we have in the YUV buffers, and then we allocate the memory. Now the image buffer, again, we allocate it only once. So only if the image buffer is null, we are allocating the memory once. And then we need to copy from this uint8 list into the image buffer, which is pointer to uint. So again, we are going to use the asTyped list method to get a pointer to this chunk of memory, but using the uint8 list interface. which gives us the set all. So the first thing that we are doing is we are copying the Y buffer into bytes. And on iOS, this is all we have to do, because on iOS, the Y buffer is actually the BGRA buffer. So we are done on iOS, but if we are on Android, we also need to copy the U and V buffer. And now for OpenCV, we need to swap the U and V buffer. So we are first copying the V buffer, and then we are copying the U buffer. So the first set all is from position 0. Then we are copying from position Y size after the Y buffer. And then we are copying from position Y size and plus V size. We are putting the U buffer. So now bytes contains all the 3 buffers, and remember that this bytes is essentially pointing to the same memory as this image buffer is pointing to. So we can call to the detect method, passing the width, the height, the rotation, our image buffer. If it's Android, we are passing true. For the isYUV parameter, on iOS we pass false. And then remember that we have this out parameter. So in order to pass this out parameter, we allocate a single integer. So we are allocating one integer, and out count is a pointer to int32. So we just pass it as the last parameter. And we get the response, and again the response is a pointer to float, so we need to convert from pointer to float 32 list. And the way we do it is we just call to the asTyped list, and the asTyped list needs to know the number of elements in the pointer. So this count we actually take from the out parameter, so that's why we need the out parameter. So the count is the value of our out parameter, and before we return, we allocated this out parameter, so we free it, and that's it. This is how we expose our methods from the plugin to the Flutter application. So now let's actually use this code inside our application. So this is our application, and let's go to the Init Detector code, and we'll copy here a new code that actually use the code that we have in our plugin. So let's import. So this is our native OpenCV plugin, and in the constructor we are calling to the init method. And what we do here, so we are reading the marker image from the embedded assets, and we convert it to uint8 list. This is how you do it. Then we create an instance of our plugin, and we call to Init Detector. The method Init Detector isn't defined on the type native OpenCV. Try correct the name. Really? Oh yeah. We need to update the plugin, so we will run Flutter pub-get. So we change the plugin, and we need to update the plugin. Okay. So now we call to Init Detector, and then our detect method. So we get a camera image from the camera and the rotation of the frame. We make sure that our plugin is initialized, and then we need to take all the different buffers from the image. And now again, on Android we have three planes, like 3 buffers, the YUV, and on iOS we have only 1 buffer, which is the entire BGRA. So first we take the first buffer, either the Y buffer or the BGRA, and then this is the 2 optionals one. So if we are on Android, we are also taking the U and V buffer, and then we just call to the detect method. And as you remember, the detect method already returns a float 32 list, so we just return this result. And finally, we have the destroy method, which we just call to the destroy method in our plugin. And now let's use this code in our detection page. This list of double darugos, this is where we are going to store all the result that we get from the detect method. And this cam frame to camera frame to screen scale, this number that we are going to compute this number, which basically the scale between the screen size and the camera frame. What's important to realize here, the detection, we are running the detection on the actual camera frame that we get from the camera, and it has a certain size. Really depends on the camera. Here we ask for the high preset, which is usually 720. So this is the preview image that we get from the camera, and this is where we run the detection on. And the coordinates that we get from the detection is actually relative to the image that we got from the camera. Now we want to draw the Aruko markers on the screen, and so we need to convert the Aruko coordinates from the camera frame coordinates space to the screen coordinate space. So it's like scaling down all the coordinates. So this number is going to be the scale factor between the camera frame to the screen, and our process camera image. So let's write a new method. So this is going to be our new method. So again, this is just a safeguard to make sure that we are still mounted, and we want to run the detection every, I lowered the number to 30 milliseconds. This is where we calculate the camera frame to screen scale, and we do it only once. We don't need to do it on every camera. And again, there is a big note here. So how you actually convert from the camera frame to the screen, from the camera coordinates to the screen coordinates, really depends on where you present the camera frame on the screen. So this is a simple conversion because I assume that the camera frame is taking the entire screen width. But if your case is different, you will find the correct way how to convert from the camera frame coordinate space to exactly where you put or display the camera frame on the screen. Then we call to the detect method, and if we got no Arukos, we just return. This is another safeguard that we are that you are doing, making sure that the result is correct. So each Aruko, each detected Aruko is expected to have exactly 8 numbers. So this is the X, Y for the 4 corners. So I'm making sure here that the length of the result is divided by 8 without any remainder. So this is a sanity check on the result. And then we just take the result and we convert the coordinates to the screen coordinate space, essentially by multiplying it by this scale factor. And once we got the new Aruko's coordinates, we call set state and put in the new list. This will cause to rebuild our call to our build function or render function, and this is where we render the camera preview, and then we, on top of the camera preview, we render the detection layer, and we pass the detection layer all the Arukos, and that's it. So what I'm going to do next, I'm going to connect my phone, because I can't run this code on the emulator because I don't have Arukos in the camera of the emulator. I'm going to connect my phone and run this application and on my phone. Okay, so here's the application, and of course it will not open the camera. This is because when we are tapping the button, we are just logging the OpenCV version. So I'm going to bring it back, and let's rerun the application. And this is it. We are opening the camera. And as you can see, we have a detection. So we are detecting the Aruko markers and we are drawing them on the screen. This is quite great. Now, if we take a look in our detection page, so here when we are calling to the detect method, this call is actually a blocking call because, as you know, in Flutter, your code is running on a single thread, and calling to the detect method is running on the main UI thread. And if this OpenCV method is going to be a heavy function, it's going to block your UI, and this is not good. So the next thing that we want to try to do is actually see if we can write this detection code on some background thread. For that, we have in Dart we have isolates. An isolate is a new thread that you can create. Essentially, it creates a new event loop that is running on a separate thread, and then we can communicate from our main UI thread or main UI isolate with the new isolate that we just created. I made here simple diagram to illustrate what I mean. So if this is our detection page, this is our main thread. So what we can do, we can create a new isolate. Now, when we are creating an isolate, we need to supply an entry point, like when you start a new thread in Android or something, you need to give the entry point of the new thread. So we need some init method in this isolate, so to create the isolate with. And in the creation method, we are going to pass as parameters the PNG marker. As you remember, our PNG marker is embedded inside the application, and we cannot access the assets that embedded in the application from the isolate. So we are going to provide it as a parameter to the init method of the isolates. And the second parameter that we are going to pass is the messages port, or what is called the receiving port. And like this is the port. So our main isolate has some port that our new isolate can communicate with. So the init method, once it will initialize the Aroko detector. So now the Aroko detector is going to live in this new isolate. So the init method is going to create a new instance of this Aroko detector, and when it's finished, it's going to send a message to the receiving port of our main thread, and in this message it will tell it, okay, I'm ready to go, and by the way, this is my messages ports. So the isolate also has a receiving port that if we want to communicate from the main thread to the isolate thread, we can send a request or messages to the isolate port. So let's say that now we want to run a detection. So we have to send a message to the receiving ports of the isolate, and in this message we will tell the isolate, please run detection, and we also I guess we will pass here all the parameters that we need, like the image and the rotation and etc. And the isolate will get this message, and then it's going to call to the Aroko detector and run the detect method, and then when it has the response, it's actually going to send the message to the receiving port of the main thread, and they tell him I ran a detection and this is the response. So we have an asynchronic request response mechanism. This is how we are going to work with the isolate. So let's start. The first thing that we want to do is go to our Aroko detector. So now the Aroko detector is going to be part of the isolate. We will not create an instance of this detector from our application. So we can convert this class to be a private class. Okay, we got a warning that it's going to be a private class, which is okay. And then this is going to be our entry point for the isolate. So as we said, we need to define here some method that is going to be the entry point. So this is going to be the function that is going to be our entry point. Now in the request that we are going to receive from the main thread, we need to get the marker and the port. So instead of passing two parameters, actually we cannot pass two parameters. When we create an isolate from the main thread, we can also supply one object. So we are going to define here a class, and this class will be like the initialize parameters or the initialize request. So this is it, and send port is from .isolate. So in the initialize request, we are going to get the port that the main thread is listening on. That's why I call it to main thread, and the marker, which is the byte array of the image marker. This is just the constructor. Okay, so the next thing we want to define create our detector. So we'll hold the reference to the detector, and to the detector we are going to pass the marker PNG. So currently our Aroko detector doesn't get anything in the constructor, so now it gets the marker PNG, and we'll take this marker PNG and pass it to the init method. So here we cannot read the marker PNG from the embedded asset. We will just take this to here, and we don't need this. And so this is how we initialize the Aroko detector inside our isolate. And then we also want to save the port to which we are going to send messages to the main thread. So this is to the to main thread, which is a send port. And then in our when we initialize our isolate, we want to listen to messages from the main thread. So what we are going to do, we are going to create our receive port, and this receive port, this is where we are going to get messages from the main thread, and then we are going to listen to messages from the main thread, and whenever we get a message, we are going to call this handle message method. So this is going to be the handle message method. We will get to this method in a minute. So we are listening to incoming messages from our receive port, and then we reply to the main thread by sending a message on the port that the main thread is listening on, and what we pass as parameter is basically our receiving port. So for each receiving port, we have something that is called send port. This is very complicating, a very confusing name, but essentially what it means, this is the port to which the other side needs to send messages. So this is like the incoming port of this receiving port. So we send it to the main thread, so the main thread will know how to send us messages. So we initialized our OpenCV detector, and our isolate is up and running, and we are listening to incoming messages. Now the main thread wants to send us a message. So we are going to define here a class which is going to represent a request that we get from the main thread. So just here below the request, we are going to define a request. So each request is going to have some request ID, because the communication is asynchronic. So the main thread is going to send us a request with some request ID. We are going to handle the request and send a response back to the server, not to the server, a response back to the main thread. And in the response, we are going to tell it this response is associated with this request ID. Also part of the request is a string. This is the method name that we want to invoke, and the dynamic, which is just parameters for this method. And like we have a request object, we also have a response object. So this is the response object, and what we have here is the request ID. So this response is associated with some specific request ID, and dynamic data, which is the response data. So once we have this, let's look at the handle message. So this is where we handle incoming messages from the main thread. So we make sure that the data that we got is of type request. Then we check what is the requested method. If it's the detect method, so we check the params that we get from this message. So the first param that we expect is image, and we expect it to be of type camera image. The second parameter that we expect is the rotation. Once we have the image and the rotation, we can call to the detector, to the detect method, and get a response. If it's the destroy method, we just call to detector destroy, and any other method, it's actually an error because we don't expect any other method. So we run the requested method, and then we are sending the response back to the main thread. We're creating an instance of the response object. We are passing the desired requested ID and the response object as data. Okay, what is this error? Oh, semicolon. Okay, so this is our new Aruko detector, and basically this is just going to be run as an isolate. So now let's get back to our main thread where we need to interact with this isolate. So we can do everything in the detect page, but it will make the detect page more complicated. So instead, let's create here where we have the Aruko detector. Let's create a new file, and we call this file Aruko detector async. So this is an async version of the Aruko detector, and this code here is going to be used in the main thread. So let's just copy the detector async, and let's see what we have here. So we define a new class, Aruko detector async. This class, we are going to create instance of it in our detection page. We have some variables, whether the Aruko thread is ready. This is going to be the new isolate, the new background thread that we are going to create, as the send port to which we need to send request to the isolate, the request ID, and here we are going to hold the map between request IDs and their completer, basically their promise. So every time we are going to send a request to the isolate, we are going to create a promise, and we are going to wait on this promise. Once we get a response from the detector, we are going to fetch the promise from this map and resolve it. Let's take a look at the init detection thread. So we're calling this method from the constructor. The first thing, we are creating our own receiving port. So this is the port on which we are going to get messages from the isolate, and we listen to messages from it. Every time that we get a message, we are going to call, anytime we get a message, we are going to call to the handle message function. And when the port where the port will be closed, this is the on done callback. So we say that our Aroko thread is not ready anymore, and this is how we spawn the isolate. Now this is the wrong code for creating the isolate, because if you remember, here in the Aroko detector, our init method expect to get this init instance of this init request class. So Aroko detector, I think, and so we fetch the marker PNG from the bundle. We create an instance of this init request, and this is what we are sending to the new isolate. So we spawn the isolate, we give the init method as the entry point for this isolate, and we are providing this object as parameter to the isolate. And this parameter contain our listening port and the PNG marker. Let's take a look at the detect method. So the detection page is going to call this detect method, passing the camera frame and the rotation. And this method returns a promise, a future, that will resolve to a float 32 list with all the coordinates on the Aroko. So if the detection thread is not ready, we are just returning null. And then we need to send a request to the isolate. So we get a new request ID. We create a new promise, like a new completer. We save this promise, this completer, in our callback map using the request ID. Then we create an instance of the request object, giving the request ID, the method name, which is detect, and the parameters. And the parameters, if you remember here in the Aroko detector, for the detect, it expects to get an image and a rotation. So here, this is what we pass, the image and the rotation, and we just send this message to the detector isolate, and then we return the promise, we return the future, and that's it. Let's look at the destroy method. So in the destroy method, what we do, we don't return anything. It works a little bit differently. First, we mark this thread as not ready anymore, and this is, again, we just create. We get a new request ID. We created the future to wait on this specific request. We save it to our callbacks map. Then we send we create the request message with just the method destroy, and we send it to our isolate. Then we are waiting here for the response from the isolate, and once we got the response from the isolate that the destroy method completed, we actually kill the destroy thread. We kill our isolate, and only now we are finishing this method. So when we are going to call this destroy method from the detection page, it will finish only once the detector thread is killed. And handle message. So this is the message that handling the responses or messages that are coming from our isolate. So we have two different modes here. If we look at the isolate in the init method, so the first message that the isolate send us, it just contains the send port, like the port that we need to send messages on to this isolate. So here in the handle message, if the data that we got is actually a send port, so we know this is the response of the initialization. So we save this port, as the port onto which we need to send messages to the detector thread, and we mark this boolean as the Aruko thread is ready, and we return. And any other response, we expect this to be a type of this response class. And then what we do, we just take the request ID from the response, and we are looking for this request ID in our callbacks map. And if we found one, we call to the complete method. This is like resolving the promise and providing the response data. And once we complete, we remove this future or this completer from our callback. And if this is not a response, so we got an unknown message from the Aruko detector, this is not expected. So that's it. This is our Aruko detector async class. And now let's use this Aruko detector async in the detection page. So we cannot use the Aruko detector, so we are using the Aruko detector async, and let's import it. And here we will create the Aruko detector async. Another variable that we need to introduce here is whether a detection is currently running or not, because the detection now is async. So we need to make sure that we don't call the detect while another detection is actually running. So we will have this boolean here, like that. And now in the process camera image, so if detection in progress, we don't want to call to detect again. And now when we call to the detector, so we are going to set this detection in progress to true, then the detect method returns a future. So we can use a wait. So now we get the response, and we can set this to false. And that's basically it. So now now we can run our application and see if everything works as expected. Okay, so let's open the detection page, and yeah, detection still works. Now let's go back. Okay, we got an error. So set state called after dispose. Okay, so if we think how it's possible, at the detection page, we see that we call set state here, and we got an error that this set state was called after dispose. So remember that now the detect method is async, so it's possible that we call to the detect and we wait here for the detect response. In the meantime, we go back in our application, so the dispose method of our widget, dispose widget of our widget is getting called, and then we immediately get a response from the Aruko detector, and we continue with our function, and eventually we are calling to set state, and this is what caused the exception. So in order to protect against this, here we check if the response is null. We can also make sure that we are mounted. So if we are not mounted anymore, let's stop here. And talking about the dispose method, so let's take a look. So in the dispose method, we dispose the camera controller, and we also call to the destroy method on our Aruko detector, which should free all the memory associated with the Aruko detector and kill the isolate itself. So let's test our application again. Okay, let's open the detection page. We have detection. Let's go back. Open detection again. Let's go back. Open detection again. And let's go back. Okay, it seems to be working fine. And that's it for our Aruko detector. We tested it on the Android app, and it works. So what we have to do now is we don't need to write anything new for iOS. We just need to set up our iOS application to be compiled with OpenCV and to compile the actual Aruko detector classes. So now I'm on my Mac, I'm cloning the repository, and the next thing we are going to update the podspec file of our native OpenCV plugin. So we will delete the old podspec file, and then we are going to copy the new one in which we basically add OpenCV as dependency, and we also update the minimum iOS version to 11. So this is the OpenCV dependency, and this is the iOS version 11. We also add a model map, which we need, and note here that the files are taken from classes. Now we are going to create the model map file. Now I'm not really sure why we need it, but it didn't work without it. So we just add an empty model map file. The next thing that we want to do is to install the plugin on our project file, and then we are going to update the pod file of our Flutter application, setting the platform to 11, the minimum version of iOS to 11. Then we are going to the iOS folder and run pod install. Now we will open our project in Xcode. So we are selecting the runner workspace file, and then we will add a camera permission to the info plist file. This is what we do here. So we will just select add new lines, select the camera permissions, and we will add some dummy description. And the only thing that we need to do now is just add the C++ file. So we need to add the native OpenCV and the Init detectors. So we are adding a new file. We are going to select the native OpenCV CPP file. Note that these are the same files that we used on Android. We didn't have to change anything. So this is the Init detector, CPP and H file, and that's it. Now let's run the project. So here is our application. Let's open the camera, give permissions, point the camera to some Aruco marker, and as you can see, it is detected. So we didn't have to change any code, just set up OpenCV with our application. And this also concludes our tutorial about OpenCV and Flutter. Hope you enjoyed it. Thank you. Bye bye.